Well, welcome to Wave Club, everybody. Um, I'm one of your hosts here. I'm Josh Jacobs. My co-hosts in organizing Wave Club are Bard Ehrman from left to right here, Bard Ehrmantraut, Uma Mohan, and Irfan Zabeh. Thank you for joining. For those of us in North America, this is a little bit of a different time. Um, Thanks for joining us at this early hour. My family's cooperating upstairs, which is really great. Um, our speaker today is Joon-Young Moon. Joon-Young is joining us in the middle of the night over there in Korea, in South Korea. So Joon-Young, thank you for joining us so late. Joon-Young is at Sungkyunkwan University in Korea. He's going to give a talk today for us on uncovering real-time brain dynamics, subsecond transitions between top-down and bottom-up modes across diverse brain states. Um, excuse me. And One thing about his talk today, he it kind of has two parts to it. So he was telling us before when we were going to get started that we're going to have like a Q&A period kind of halfway through or something roughly like that. Um, I guess if you have questions, you can put them in the chat, and Irfan and Uma and I will help coordinate the Q&A. We're not using the Q&A feature, so just right. So we'll just put them in the chat if you can. Um, and um, And I think I will turn it over to Jun-Young. Um,
Okay.
oh, I'm sorry. Here's Jun-Young's
Ah,
biography. Um, uh, he's a principal investigator at Sungkyunkwan University in Korea. Does work on brain state dynamics and transitions with computational modeling, doing work on conscious and unconscious states, um, using computational models and network modeling of a lot of different kinds of data, scalp EEG, MRI, intracranial recordings as well. And I'm going to turn it over to him now. So, Jun-Young, thank you for joining us in the middle of the night here. Um, and just this last slide is a reminder for me to tell you that all of our recordings of Wave Club are posted online on YouTube. And in case you want to go back and get a sense of what we talked about in the past, what past presenters had talked about. It's a really nice resource for people getting up to speed with the field. And follow us on Blue Sky. We're at Wave Club Seminar to get a sense of upcoming talks. So I'm going to stop my screen sharing and turn it over to Jun Young. Um, Thank you again for coming today.
yes. Hello, everyone. Well, good morning, afternoon, or evening, depending on where you are. And also, thank you very much for the introduction and this occasion. Um, it is my pleasure to be here. And as you will see, this work is very much in progress and also in its expansion. So I look forward to many comments and many feedbacks from the great traveling with people in this seminar. So the title of the talk is Uncovering Real-Time Brain Dynamics. Especially, we will be looking at the subsequent transitions between the top-down and bottom-up modes, and by which I mean that the top-down mode refers to the flow from the higher order cognitive areas to the sensory areas, and bottom-up is in the reverse direction. Uh, okay, so these are my current and previous lab members, and they are the ones who are doing the actual work. And especially for today's talk, these four members have contributed the main methods and the researches, and then my collaborations, Christopher Honey from Johns Hopkins University, and then Un-Chul Lee and George Marshall from University of Michigan, and then my fellows at Sungkyunkwan University, Seok-Jun Hong, Hanbyul-jo, and then also Jae-Young Ho from Dartmouth College. He's done the modeling part of the current work. So in our research, I mean, in general, we typically begin by developing or refining a methodology and then apply it to real data and finally extract a conceptual and theoretical insights from the results. So in other words, methodological innovations often enables us to observe new phenomena and ultimately formulate new theoretical perspectives. And today's talk will follow the same structure. So I will first introduce the methodological framework. And then using that framework, we present experimental results. And then finally discuss the conceptual ideas that emerge from these findings. Our research program is motivated by the idea that the understanding the dynamics of brain in real time will be crucial to identify and monitor and ultimately control brain state transitions. So for example, the examples shown here are possibly two brain states which are most different from each other, one in the conscious awake state and the other in unconscious anesthetic state. So when we are conscious, we can hear, understand, and have thoughts, and we are unconscious, we cannot. And these movies demonstrate brain dynamics in real time with a measure we developed called the relative phase analysis. So you can see that the patterns are very different from each other. And in upcoming slides, these will be the patterns and these will be the dynamics that I will talk about. So again, we developed a method called relative phase analysis or relative phase method, which is a real-time measure. And then by which I mean that we can compute it for the every time points of the given data we have, given time series we have. And it is also a global measure. So you don't have to choose a set of channels. You can just apply this method to the entire channels or entire voxels of the data set you have. And using this relative phase method that we found that our primary finding was that it, the brain constantly fluctuates between top-down and bottom-up modes at the subsecond scale. And the scale that I'm talking about is about 200 or 300 milliseconds. So that will be our primary findings. And then utilizing this method and then utilizing these findings, we show that such transitions correlate with the level of consciousness, and then such dynamic characteristics also correlate with the fMRI functional networks. So the second part will be connecting the EEG and the fMRI via simultaneous EEG fMRI recordings. And the third part will be looking for the group differences between typically developed and the ADHD population. I do have a model to share with you at the very end, but I think I will be getting questions before I go to the model, maybe. Okay, so again, going back to the start. So let's say we have a EEG data at our hand. So this is the 128 channel data, eyes closed state, and then we performed the bandpass filtering and only the bandpass filtering. So we are looking at the alpha wave, and we didn't do anything else. No other pre-processing. And then when you see the activity, when you see the dynamics, it seems like there is a certain kind of pattern. Maybe it's traveling from one area to another. Essentially, it just comes down to the nonlinear time series analysis, where you have multiple channels. We can either look at the amplitude and the phase together, or we can choose to analyze one of them. For example, we can only look at the phase, just so we can differentiate amplitude and phase, and then take one of them and look at them. So this is a transform, mathematical transform that's called as a Hilbert transform, and we are looking at the Hilbert transformed dynamics. So, and each circle, each node represents the signals from each channel, and they are curved from the anterior to the posterior. And then, as you can see, there's some kind of dynamic patterns. The idea for us is that maybe phase is good enough to give us some genuine information about the dynamics, and that's the where the relative phase method comes from. And as illustrated in the figure, the relative phase method is based on the idea that given set of signals, we can infer the temporal ordering by examining the phase lead-lag relationship. So by looking at the phase differences, maybe we can look at which signal comes from, and then which signal comes later. So maybe because we can look at the time order of given signals, maybe possibly we can infer the information flow from the signals that's ahead to the signals that's following. So that's the idea. Okay, so again, in the beginning, we perform a mathematical transform called Hilbert transform. And at each time point, by Hilbert transform, by this mapping, we can define the phase and amplitude of given waves. And usually the amplitude has been the focus of research. For example, like from 1960s and 70s, there is a studies about microstates looking at the global amplitude pattern. But again, for this study, we focused on the dynamics of the phase, and this is our definition. So after defining the phase of each wave at each time point, we sum the phase of the entire system, and that will be our center of the mass per se, or the average phase of the system. And then we subtract that average phase of the system from the absolute phase of each signal. So it's really relative phase. Last but not the least, we take the sign of it. Actually, we don't have to take the sign. The relative phase itself will give us a good deal of information. But the taking sign gives us some advantages. So this is motivated by a measure called WPRI, which I'm going to talk very briefly at the later slides. Basically, you are taking the imaginary components, and basically you are giving a nonlinear function to the relative phase. So if the phase difference is 90 degrees, you're going to map into +1. And if the phase difference is negative 90 degrees, you're going to map into -1. So if a channel's signal is phase leading with respect to the mean phase of the system, it's going to have a plus sign. And if it's phase lagging, it's going to have a negative sign. So for example, given these red and blue waves as examples, you can intuitively feel that the red wave is phase leading the blue wave. And then by giving this relative phase measure to these red and blue waves, that you can see that the red wave has a nice mapping to a positive value, which means it is phase leading, and the blue wave has a nice mapping to the negative value, which means it's a phase lagging with respect to the center of the system, the mean phase of the system. Okay, so we can do that. So we can assign this relative phase value to the every channel of the given system. And then after performing interpolation or extrapolation, we can end up with a topographic plot of this phase leadness across all the channels in the system. Again, the red color, will mean that they are phase leading with respect to the mean phase of the system, and the blue color will mean that they are phase lagging with respect to the mean phase of the system. And because we are utilizing Hilbert transform, we can get the amplitude and phase for every time points, every time frame. And basically, essentially, we end up with a movie with the topographic relative phase patterns. So that's our end object. And with these movies, we are going to study the dynamics across different modalities, across different sessions, different tasks. Before going further, so we did some comparison against this relative phase method with some known measures such as Grant causality or maybe transfer entropy. And this was a model study. This was a model study. So we utilized either a grammar model or Stuart-Landau model on the structural brain network, and then see if this relative phase will give similar results against other two measures. And then, yeah, it turns out that, well, of course, the Grant causality and transform entropy requires a time windowing. You need to make a window, a time window for the data, for the time series. And then so same for the relative phase, even though it does not require for us to define a time window to compare against other methods, we utilize time windowing and then compared with these other methods. And the correlation was about anywhere from 0.7 to 0.9. So relative phase was a good proxy, at least as far as the model data goes for the Grant causality or transfer entropy measures. And comparison against other measures too. So among the brainwave analysis, there has been traveling wave analysis utilizing the phase gradient. For example, this paper by Mohan and Jacobs. And also there has been a tradition of time window based phase measures. So for example, PLI, phase lag index, or DPLI. For example, this paper is from Stam and Van Straten, and it measures whether two signals are locked with respect to phase lead lag or lagness within given time window. So what we can do is compare our relative phase measure against these traveling wave measures and the time averaging phase measures. So this is the relative phase of given time window. And when we compare with either the variations of the time averaging phase measures, directional weighted phase lag index, or we can also choose a set of channels, so right at the center of the brain, and then apply the usual the phase gradient method, and then see if by looking at the peaks, basically we're looking at the peaks and troughs, whether the signal is propagating from front to back or back to front. And then when we compare, of course, in doing so, we also utilized again a time windowing. And the correlations were generally very high, anything from 0.8 to 0.9. So again, the relative phase measure seems to be a good measure that combines the results from the traveling wave analysis and then also the phase-based measures. Okay, so in previous comparisons, we always use the either time windows or actually both time windows, and we chose a set of channels. So, but the utility of this relative phase method is that you don't have to utilize time window, or you don't have to choose set of channels. You can just apply it to the channels in the entire system, and you can look at the global dynamics. And that's what we did. So again, going back to the movies at the very beginning, we applied our method to the awake state and then anesthetized state. And then again, there is a very noticeable difference in the relative phase patterns. So if you look at these patterns frame by frame, you see that in the unconscious state, in the deeply anesthetized state, it seems like the pattern is almost random. Whereas in the awake state, there's a certain patterns that is dominant. And then, well, one of the maybe popular, one of the easiest method to cluster those patterns, like what kind of patterns are dominant throughout our movie, throughout our dynamics. we utilized the K-means clustering of this EEG topographic relative phase patterns, and then we end up with the four dominant modes. So we could use Davis Boolean index or other indices that will give us the optimal K, and that K turns out to be almost always four. And then these four are the dominant patterns. And I mean, you can see in this example that the front area phase leading and the parietal area phase leading, they are the dominant patterns. And also they were kind of like a transient state. The left area phase leading and the right area phase leading. So these were the four dominant states. And actually, we can also perform PCA. We can also perform PCA across these time frames, across time. And actually, in simple cases, the principal components from performing such PCA is more or less equal to the applying K-mean clustering. And as you can see, the principal components that we get from the PCA is very similar to the centroid that we get from the K-means clustering. The correlation between these patterns is like 0.99. And again, we can utilize this principal component analysis and we can perform a linear regression. So by which I mean the y-hat here will correspond to this each frame, each time frame. And these modes could be either, so the regressors could be either principal components or the centroids. And essentially, because they're essentially the same, so the first regressor can be the first principal component, and then the first principal component. So in its positive side, it corresponds to the mode one front-back phase pattern, and in the negative side, it will correspond to the back-to-front phase pattern. Again, for the principal component number two, it's either left to right or right to left. And then if we use them as regressors, the beta 1 and beta 2 will give you the degree to which each frame can be classified as a mode 1 or mode 4. I mean, if beta 1 is positive, it will be classified as mode 1 in K-means clustering, or mode 4 back to front in the K-means clustering. So by just looking at beta 1 and beta 2, so this is time series for beta 1 and beta 2. So we can identify at each time point the dynamics of our movie, the dynamics of our relative phase. Okay, so simply we could just look at the occurrence. So occurrence of each mode. So how often these modes appear, or we can also look at the dwell time, and then also we can look at the transition matrix, the probability from one mode to another. And this was the general results that we get from the resting state. The mode 1 and mode 4, these front back and back to front, they are the dominant modes. They occur about more than 30% of the time each. And in between them, there are transient mode, left to right and right to left, that occurs about 10% of the time. And the characteristic length of each mode, the dwell time of each mode, appears to be about 200 milliseconds. So that's why we called it subsecond fluctuations between two modes, front to back and back to front. Okay, so now for the resting state, we know that the brain fluctuates rapidly from front back and back to front mode. And what do they mean? What does they mean? So first, since we have the general anesthesia data, the participants being anesthetized by general anesthetics. So the LOC means the loss of consciousness, and the ROC means the recovery of consciousness, and the burst and suppression period, they are like deepest unconscious state. They're the deeply anesthetized states. And we can study the relative phase dynamics of each mode by looking at the mode occurrence or the probability density and the dwell time. So we have a occurrence for each mode 1, 2, 3, 4. And also, if the error is too high in our linear regression, which means that that time frame, that time point, the pattern could not be identified as either of one of those four modes, we classify them as other. And our finding was that the occurrence of these four canonical modes, especially the mode 1 and mode 4, they were the highest. They were the largest in the fully awake state. And as you lose your level of consciousness, and as you go to the deepest level of unconscious state, uh, the dominance of these modes goes away, and it becomes almost random. So that was our finding. And of course, the advantage of the principal component analysis, the advantage of PCA is that you can always calculate the eigenvalues of each PC. And as you can see here, in conscious state, in eyes closed conscious state, the eigenvalues from two PCs, again, which means that these four modes, because the first PC represents this front, back, and back to front, and the second PC represents left to right, they contribute about 80% of the explained variance. Whereas in the unconscious state, you need about 12 or 13 principal components to make up the 80% of the explained variance. So which means, again, it becomes almost random in unconscious state. Or using the inverse participation ratio, which just tells you how dominant the pieces are. It will give you reliable differentiations across a distinct state of consciousness. So every data you've seen here so far is based on the alpha wave, but the results does not only come from the alpha wave. You end up with a similar dominant for canonical modes, especially the bands that's near to the alpha band in the theta or low beta or even high beta band. So the dominance of the first principal component is highest at the alpha band with about 55%, but it's still very large in all the lower bands, around like maybe 45%. Again, we did this for the resting state. So if given tasks, the dominance of alpha band might change either to maybe theta or low beta, and that's one of our conjectures. So that was the anesthesia part, and then now we move on to the simultaneous EEG fMRI part. So utilizing simultaneous EEG fMRI, we measured the EEG and the fMRI at the same time. And the EEG result you see here is a group averaged result, session averaged first, and then averaged across participants. So in doing so, all the subsequent fluctuations would go away, and what remains will be the seasonal trend of the fluctuations that has a characteristic time scale that's much longer than subsecond scale. And the reason for doing group average will become apparent in the later slides. The task that we gave them is very simple. It's a resting state for 20 seconds, followed by checkerboard watching task for 20 seconds. And the reason why we set up the task with a very strong visual stimulus is that because we already know the answer. We already know these tasks will activate V1 area very, very much as compared to the resting states. This is the bold activity during the resting period, and this is the checkerboard period, the activity from the checkerboard watching period. And this is again the group averaged relative phase during the resting period and then during the checkerboard period. And as you see, they are very different from each other. So we can actually calculate the correlations of this EEG dynamics, group averaged EEG dynamics against the bold activities. So in order to make these calculations, because their temporal scale is very different, as you may know, as you know very well, that the bold dynamics has a inherently very slow time scale. So this is the correlation between the beta, the regression coefficient. So this gives us the degree of how each frame could be accounted by the regressor. In this case, the regressor will be the front-back mode. So if the correlation is very high, that means that the bold activity from these areas are highly correlated with the front-back mode of EEG relative phase pattern, and vice versa. If the correlation is negative, that means that these areas are highly correlated with the back-to-front pattern in the EEG. So now if you look at the correlations, the highly correlated area, so this is a year 17 passellation for the fMRI functional networks. So all the higher order areas, the default mode network A, B, C, and then the frontal parietal network ABC. So they are all higher order areas residing in the maybe prefrontal cortex and also in the precuneus, the parietal cortex. So they are all highly correlated. The correlation is above 0.4 with the front to back mode. And the V1 area, is highly correlated with the back to front patterns from the EEG. So this is reason why we use the checkerboard stimulus, because we already know that it's going to stimulate the V1 area. And we wanted to check if that V1 activation is correlated with either of each patterns, and our conclusion was it is indeed the checkerboard stimulus. It is indeed correlated with the back to front pattern, and during the resting periods, the excitation of the higher order areas are highly correlated to front back pattern. So that's why I had the title in the beginning, and that's why we called this front back pattern as the top down mode, and then back to front pattern will be bottom up mode, because they are each associated with the activation of the higher order cortical areas and the lower order sensory areas. So far, the analysis has been done on individuals with different brain states, for example, in different states of anesthesia, or in different tasks, resting versus checkerboard, flashing checkerboard. So now we performed it in different groups. So control group against ADHD, especially inattentive type. And then the reason why we especially looked at the ADHD inattentive type was that one of the theories behind why there is an attention deficit in the ADHD inattentive group is that there exists an imbalance between top-down and bottom-up mode. So the top-down doesn't work really well, and it fails to inhibit bottom-up modes. So we wanted to see if that theory is captured by our canonical mode dwell time or occurrence rate. So this is the relative phase again, alpha wave for the typically developed and ADHD. And you may, you can notice, maybe you can notice that the ADHD group has indeed slower transitions and stays a bit longer in bottom-up mode or back-to-front mode. And that is shown in the probability density or the occurrence rate, and also in the dwell time. So these are from the eyes open state, and the yellow shaded areas, they represent the results from the eyes closed state, and both in eyes open and eyes closed states, the occurrence rate for the back to front mode or the bottom up mode is significantly higher, about 30% higher for the ADHD group, both for the occurrence rate and both for the dwelling time. And again, I think this confirms one of the theories of the attention deficit, that there is a failure of inhibition of the top-down mode, therefore the bottom-up mode becoming too dominant. And then we could see if this relative phase analysis could be used as a marker, a biomarker for the successful diagnosis of whether the participants is indeed ADHD or typically developed. So there is also existing measures called TBR, theta to beta ratio, which looks at the power of the theta band and the beta band. And for some subpopulations of ADHD types, it is known to work somewhat. And but for the inattentive type, it is already known that it doesn't really give you the statistical significance, and as that's shown in here, that's confirmed here. And then we tested the ROC curve, which gives you the successful true or false rate of the relative phase measures. And then yes. Either using bootstrap or not, it gives you a significantly higher successful rate of a prediction. So again, I think the reason why the relative phase could tell the difference is because it accounts for the mechanism behind the attention deficit. Okay, so that was the method. And then the applications of the method to the experimental data. And then now is the part for the conceptualization, some of the ideas. So what is this top-down and bottom-up transitions? So well, I cite the Chris Honey's paper from 2017. And then in this paper, the hypothesis was that the transitions between two dominant modes, in this case, it's internal versus external mode, it can be a crucial mechanism facilitating learning and memory and perhaps everyday task and even attention. So in the internal mode, let's begin with the external mode. So in the external mode or bottom-up mode, the brain is driven by incoming sensory information, and then information flows from the lower to higher areas. And in the internal mode or top-down mode, the brain uses the prior information to build and continuously update on internal mode. And the key is that this top-down bottom-up mode operates in fluctuation. So there is always a bias to one of these modes. And this top-down, bottom-up, or external-internal fluctuation occurs in all scales, temporally and spatially. So in this paper, the observational evidence is well summarized. So beginning from wake to sleep cycles. So the conjecture is that the wake stage would correspond to the more of external mode, whereas the sleep period would correspond to more of an internal mode where you could internalize all the experiences you gained while you were awake. So that goes in 24-hour cycle. And then beginning from there, there is a subsequently shorter temporal scale fluctuations, and also there's a, so in the sleep versus awake fluctuation, you utilize your entire body, and then also the spatial scale goes smaller, becomes smaller and smaller. And I think what we found from EEG is that at about 200 millisecond scale, there is a subsecond cortical top-down and bottom-up mode fluctuations in the information flow. And our hypothesis is that that may be what's being shown by our relative phase analysis. So to sum up, we suggest we developed this relative phase analysis, looking at the phase differences of each signal with respect to the mean of the system. And by utilizing this very simple idea, simple measure, we were able to identify 4 dominant modes, and then subsequent fluctuations between front to back or top down, and bottom up or back to front mode, and then showed that it correlates with the level of consciousness, and also correlates with the bold activity of bold functional networks. And then there's a group difference between the typically developed and then ADHD group. So I think this is a nice time to get some questions before I move on to the next set of results. Okay.
It looks like there was a clarification in the chat about which bandpass frequencies you use.
So yeah, the results shown are the alpha band mostly, but again, it's the results are about the same in the theta or lower beta band. Yeah, and being EEG, we couldn't go up to the gamma band, but well, that was our results. Yeah.
What does that mean that the results are similar for other bands?
Okay, so let me go back. Yeah. Okay.
Like, does it mean that
We have dominance of 4 mode in our other band too. Let me go back to the slide. So yeah, okay.
it looks like Daniel has a question, was asking about this too. Daniel, you can turn on
Mm.
your, we're an informal group today. You can turn on your camera and talk if you want.
So the dominance of 4 mode is highest at the alpha band, but it's still very high in the neuro band. Uh, s- we also looked at the correlations between this beta 1 and beta 2 across different bands. The correlations were not very high. So, I mean, because we mainly focused on the resting state, we cannot really tell, like, so maybe in the lower band, there's a top-down dominance, and then in the higher band, there's a bottom-up dominance, which occurs at the same time against a certain set of external stimuli. We could also test that given set of good external stimuli, locking stimuli, and that's one of our. Well, actually, we do have some results with respect to external stimuli, so that's to be followed. But uh, so that's what I mean by we end up with the same similar results. We do end up with the 4 different mode for other bands too, the dominance of 4 different mode, but the dynamics for each band seems to be different.
Why don't you continue. You have some more slides. Why don't you continue on with the second part of your talk, and then we can have more Q&A at the end. I want to make sure you have time for everything.
Okay, sure. Okay, let's go there. Okay.
We can keep talking about this frequency band issue later, and I think
Okay.
Martin had a question too. But
So I'm going to give you like bits and pieces from my current analysis. So first, some examples from uh, real interesting interesting tasks. One of them, the first of them is the global local audible paradigm from yeah, Dehaene and Bekenstein. So okay, so sounds in 5 bits. The fifth note is different, and that's local audible. But sometimes the fifth note is not different. So that's the global audible. So that's what they call local versus global. So the local audible, for the local audible, so the fifth note is different from the four subsequent notes. So you don't really have to know all the context. But for the global audible, I mean, the pattern itself is different. So you have to know, you have to have the prior about the context. So that's the local and global audible paradigm. And it is already known that the global audible or the global deviant will induce P3 or P300. So event-related potentials here. But if you look at the relative phase, you can see that there is a bottom up, more of like a center phase leading, and then top phase leading. So maybe top down, and then I think this shows you that with respect to the auditory stimulus, it is not the parietal area, but probably the central area where it is close to the A1 area. That is phase leading. So it is just a very simple analysis showing that we can observe the uh, modulations of a top-down versus bottom-up mode, or we could do something like event-related dynamics, looking at the information flow changes by utilizing the relative phase, even in like a millisecond, like hundreds of milliseconds order. And of course, we don't see these changes in the local deviance at all. So that's one of the tasks. And the second one is the GRAD-SPT, gradual continuous performance task. So this is how it goes. So the picture changes gradually in every 800 milliseconds. And then mostly they are CT, but about 20% of the time they are mountains, they are natural scenes, and you should not click your button when it's mountain, but you should click the button on when it's city. And it's a very difficult task because the picture changes in every 800 milliseconds, and you do it for like 8 minutes. So your attention dwindles away. And then by looking at the response time, um, you can dissociate the periods where you are in the zone when you are focused, or out of the zone when you're zoned out, when your attention is going away. Maybe you are mind wandering in those periods. And then we also see that there's a difference between this relative phase pattern between zone in and zone out. So there is a more of a top-down dominance in the zone in at the crucial 800 millisecond period. And there's a zone out dominance. In the zone out, there's a bottom-up dominance in the zone out period. So that was another task. We could see the difference between zone in and zone out. And then the Woo Jae-hyung, our collaborator, did a very similar model study utilizing either grammar model or Stewart-Landau model on the structural brain network. And then the grammar model is it's a nice model that could be our first approximation to more complex oscillators. And then what we observed was that based on our structural brain network topology underneath the coupled oscillator system, we actually end up with the front lead or parietal leading phase lead lag patterns. And then in our parameter space, by just giving a random walk or Ornstein-Uhlenbeck process, biased random walk between our parameter space, we end up with a nice model results. This is a comparison of the mode occurrence, the empirical results, and then the OU process, the random walk with the grammar model of the occurrence, and then dwell time. So the main point was that based on the brain network topology, this top-down, this front reading and parietal reading patterns naturally occur spontaneously. So that was our modeling. And then, well, this is David Marr's classical 3 levels of analysis, and our modeling would go at the implementational level. Given a coupled oscillator systems, would they occur naturally? And then perhaps more interesting point will be going one level higher in the algorithmic model. The Van Roolen and Alamir also wrote a paper about the making interchanges between the predictive coding or predictive processing ideas and this front-to-back traveling waves. So that's well, I thought that paper was very interesting, and that one of the directions that I wish to go for is to go up in this 3 levels of analysis. Okay, so that's about the relative phase analysis. And then very briefly, I can give you a glimpse about why RPA seems to work quite well. And then this is a theoretical framework that I'm developing called general oscillations theory, integrating an amplitude and phase dynamics all together. So this is our schematics. So given time series, Hilbert transform, we get the phase, we calculate the relative phase. Either we do the K-mean clustering or PCA, we end up with the PC or centroid. We do the linear regression, we get the dynamic coefficient. We look at the occurrence rate, or we look at the dwell time. Let me be very brief because probably I'm running out of time. The goal is, because the oscillatory systems are ubiquitous across physics, maybe we could come up a framework that incorporates both the amplitude and phase dynamics at the same time. And also we took a sine operator, if you remember. Maybe we don't have to, or maybe we can give more meaning to that sine operator. So one of the way to expand is just do the same thing for the amplitude. But I think we came up with a better idea. We came up with something called dynamics operator-based theory. I will be very brief. So just given analytic signal, we call Z, the K will be the covariance of this Z, the Z multiplied by the Hermitian of the Z, and the H, because every analytic signal is composed of the amplitude term and the phase term, and then this H will be the covariance of the amplitude, and then this phase term will be the covariance of the exponent, this one, that comes from our Euler formula, cosine plus I sine. And in terms of operators, or what we end up with is the covariance Z, covariance K, sorry, equaling the amplitude term times the phase term, and the phase term again is made up of cosine and then sine terms. And then finally, this sine term corresponds to our relative phase dynamics. And if you look at these terms, where H is all about the amplitude, the R times the R transposed, and C is all about the phase coherence. I mean, given being a cosine function, it's going to give you value 1 if the phase difference is minimized. So the main message that I want to say is all the information about phase lead lagness is accounted in this S operator, and which is essentially the relative phase operator. So I think that's why mathematically our relative phase is capturing the dynamics of the systems that we are inspecting very well. And then we could, well, yeah, we could apply this operator analysis to the we have some nice mathematical theorems here, and we could look at the amplitude and then the phase coherence and the phase lead lag dynamics. So we could do a whole bunch of other analysis based on our this theoretical framework. And we could also do it for the fMRI. This is the result that was applied to the bold dynamics. So that's the direction for the future researches that the researches that we are performing currently. And the current researches are all about the relative phase dynamics. They are all summarized here. And the code for the relative phase analysis, they are uploaded in this GitHub. So if you are interested, you could go there and then perform the relative phase analysis on your data set. Okay, so that's it for my presentation. Thank you very much.
Thank you, Joon-Young.
This is great. We have a couple of questions in the chat. Going from the most recent, I'll ask Lyle to unmute and ask directly if you're up for it.
Sure. Hi. Nice talk. That was very interesting results. So just following up on the frequency question, what's the filter specifically and what's the roll off of that filter? And I'm asking about that just because could the similar dynamics that you observe across the different frequency bands, like alpha and theta, be due to spectral components or spectral leakage of components from the alpha band?
We used we wanted to be robust, so we tried like a various filters. We used like a very high order filter to make a very steep cutoffs, and it seemed the filter didn't really affect. I mean, yeah, you end up with dominant four modes across different bands. Well, up to 50 hertz. We didn't go beyond that. And then one of the things we could do is we could also test the same IPA relative phase analysis to the ECOG data set. And I think that will be also informative. Yeah.
Because the filter roll off is, I mean, we're talking about pretty close frequency bands, theta and alpha. The filter roll off is generally expressed in, tens of hertz. So it could be possible that there is some roll off between those two frequency bands, and it might be a consideration there. And could be an explanation for why you're seeing similar phase dynamics in the theta and alpha. So just wanted to highlight that point.
Okay. Thank you, Lyle. We also have a question from Martin Lee. I'll also have you unmute.
Hey, that was a really cool talk. I asked this, I think, earlier in the talk, but I think I saw something like this come up in your modeling. When you show the conscious top-down, bottom-up dominance, like there's some sort of like nice kind of balance that you can kind of make out, versus with like ADHD, it's like less balanced, and with unconscious, it's something very different. Do you have like a quantitative measure to kind of measure this and so you can compare it, or is it
Yeah, so yeah, that's a good question, a good point. So yeah, we do observe the different balance between top-down and bottom-up mode. The one quantity we just did like very simply was just taking the mode one, looking at the mode one to mode four ratio. One of them as a denominator and one of them as the numerator, and then it usually well actually there is also difference between eyes open state and eyes closed state, and well that's to be expected because you get stimulus when your eyes open. And then when you are watching movie, which is not shown here, there's again some differences there. But uh, the yeah the depending on the task, the ratio goes around 0.5, but it ranges between like 0.4 to 0.6. And then for the again, as you see here, for the ADHD goes to the bottom of mode even more further. Yeah.
but for
So
this it wouldn't
yeah,
ex
yeah. Mm.
oh sorry, it wouldn't extend for like unconscious. There like it
Mm.
wouldn't have more bottom up for unconscious compared to control, right? So it wouldn't be the same quantitative
Yeah,
measure.
right. So the problem with the unconscious versus conscious is there's a lot of states that could be classified neither to the mode one or mode four, or mode two or three in that matter. So there were a lot of other frames that is classified as other. So the epsilon, the error term in our linear regression was too high. So yeah, I think for the conscious unconscious transition, it's probably looking at the mode distribution with the other term included. That's probably more intuitive than just looking at the mode one to mode four balance. Yeah.
Thank you.
Thank you.
I had a question. May I?
Yes. Yeah.
Can you tell us a little bit more? So you talked earlier about how your metric was different from, I'm sorry, I forget the word that you were talking about how it was different from the kinds of traveling wave metrics that I've used in my lab's work with Uma
Mhm.
and Irfan and other people. And I wonder if you could explain a little bit more about how it's different, because it looks like the results are the phase dynamics that you're seeing are showing things that look like traveling waves.
Yeah.
Like that look like the same kinds of traveling waves that I've seen
Mhm.
in the past, where the waves are going front to back or back to front. But you were saying
Mhm.
that your metric combines time. Yeah, maybe you could just say a little bit more about what's different and what's the same
Mhm.
from your
Mhm.
metric to the kind of things I've done in the past.
Oh yeah. So the reason why I said the method is a different in terms of its how do I say its utility maybe is that the method itself doesn't really require any like time windowing. So that's different with this kind of okay uh, window-based phase measure. And one other thing that I was pointing out was that it doesn't really require, I mean, you could choose set of channels and then apply, but you don't have to choose set of channels. You could just given like given like 100 channels, or given the entire the bold data, like 60,000 voxels, you could just apply it and see with respect to the center of the mean, well, which area is phase leading or phase lagging. So that's what I meant. That's what I meant. So as compared to the classic traditional phase gradient method, looking at the gradient of the coming from the phase, I don't think it's one is better or they are compatible. This method just our method just look at the relative phase, and this whole comparison, the purpose of this comparison is that when there's a traveling wave, when there's a nice phase gradient, which could be counted as a also nice gradient from the front to back or back to front pattern. So, I mean, if you look at these equality results, the relative phase is also showing us a gradient from back to front, either back to front or front to back. And that's where the maps, the time windows are corresponding to each other from our nice gradient relative phase to the phase gradient. So in those periods where there is no such thing as a well-defined phase gradient, and then we would end up with a pattern that's also not really well defined in terms of the relative phase gradient pattern. So in that sense, I think they are comparable, and then with a good interpretation, we could make out that I mean, by looking at the relative phase, that you could say, oh, it seems like at this point there could be a traveling wave from front to back, or so forth. Yeah.
But what is an example of something that can be captured with your method that cannot be captured with a traveling wave?
Josh, I think the only difference is that one is a derivative and the other is not. Um, that's all. I mean, you get the relative phase by integrating the traveling wave analysis because one is a phase. You're looking at local phase differences as opposed to looking at relative phases,
Mm.
and I think they're equivalent.
Yeah.
So I don't think there's anything you would get from one. One you can get from the other, and vice versa. So
Okay.
So yeah, so that's a good point. So in a sense, this is a how does it like a simplification of the algorithm, making the pipeline easier, and just looking at the phase patterns directly and making sense out of it. Yeah, and then that's what I've done for the 3 data sets that came after, and then so. And then the finding was that this global pattern seems to be changing in every 200 milliseconds. So that was the main finding that I utilized out of this method, out of this pipeline. Yeah.
Okay, thanks.
Well, and then there's one more thing actually at the very end. I skipped very briefly, but this whole operator idea. Yeah. I mean, if you define this K as a covariance, I mean, the H will look like this, just the multiplication of amplitude from each channel matrix, R1 times R1, R1 times R2, and so forth. And then the C and the S operator will be the cosine difference and the sine difference, right? And basically, the relative phase is just this S operator in disguise. And then it gives you the relations between each channel, between channel 1 and 1 itself, 1 and 2, and 2 and 1, and so forth. It's anti-symmetric matrix, by the way. Anyway, and so it gives us all the interactions, all the phase lead lag dynamics of the system. And then the C will give you all the currents of the dynamics between the interactions, actually the second order interactions, because we are looking at the theta 1 minus theta 2 and so forth. And this H operator will be giving us all the amplitude interactions. And so that's it. And our relative phase actually maps onto this S operator. And when we look at the amplitude dynamics, that will be H. And all the phase currents measures, that will be more or less correlated with the C. And then actually the interesting thing about this framework is that the given Gaussian assumption, well, say the time series are Gaussian in terms of a temporal sampling, then all the cumulants, like the skewness, the cortices, they will vanish all we need is the first order and then second order cumulants, or the mean and then standard deviation, or the covariance actually. That is all need, and this because they are all like a covariance matrices. If it's a Gaussian time series that we have, every interaction like a cross covariance, cross spectral density, every interaction is contained in this framework. The question we can ask is it really Gaussian? Is the time series from the EEG or bold Gaussian? Probably it's not strictly Gaussian, and even if it's not Gaussian but bounded, the signals are definitely bounded. It doesn't go to negative or plus infinity. If it's bounded, our interaction terms like theta 1 minus theta 2, sine of it, and so forth, it will give a good first order approximation, like in tail expansion. The first term will be corresponding to our operators. So even if it's non-Gaussian, it's going to be a good approximations to the dynamics and with the error that doesn't diverge. So yeah, well, I'm arguing that there's a reason behind this relative phase formalism that captures the dynamics quite well. And sometimes the dynamics will correspond to this traveling wave patterns from front to back if there's a nice gradient that's well defined. Yeah.
Do we have more questions?
I have a quick question, if that's okay.
Please, yeah, dive in.
I'm trying to understand because so by the way, really good talk. Thank you for presenting this.
Daniel, you're a little quiet. I don't know if it's just me.
Is this better?
A little bit.
Okay, I'll try to speak louder.
Thanks.
So if you have a front to back gradient where you have, instead of one wavelength of an alpha, you have like two wavelengths, because if you do the relative phase, you might have something that the front is actually lagging with more than 2 pi. So you would consider it as like lagging, but it's actually in front of the wave, right? Because everything, all your phases are in between like pi and minus pi. So that could be like, another phase could be like between minus pi and minus 2 pi. So it would actually be wrapped around and be as lagging while it's actually like behind of the wave, right?
Yeah,
if
yeah,
you have like two wavelengths in your front to back or back to front. So how do you deal with this? And then did you do some analysis to make sure that the front to back and back to front is like not influenced by this?
Yeah, that's a very good point actually. So if the time delay itself, it's comparable to the band that we are calculating this. Like for example, if when we are looking at the alpha wave, if the delay is like more than like a 100 millisecond, which is the one cycle of the alpha wave, then we would end up with like the problem of like which comes first and which comes later. So we have to be very careful. But fortunately, luckily, the delay or the speed is fast enough. It's usually less than the quarter of the one cycle, so less than 1/4 pi. So that's a good thing. 0.5 pi. So that's a good thing. But I think we might end up with that kind of problem if we go up too high, like in the gamma wave, because the width is really too short. So I mean, in EEG we only went to 50 hertz. So up to that point it was okay. But if we go beyond, we might end up with the problems like which is coming first and which is coming later. Yeah.
So you're saying that you have mostly one cycle in your data. It's like one cycle of alpha.
Yeah.
Okay. have you looked at slower cortical potentials, like smaller than 1 hertz? Especially if you have fMRI, you could look at that too.
Yeah, so the bold was also okay. I mean, uh, the bold, the characteristic, the dynamics in the bold was usually like so when we have one propagation, it happens over a period of like maybe 10 seconds. So it's about from 5 to anywhere from like 5 seconds to maybe up to 15 seconds. So it's like really, really slow. And the propagation being slow, the say if the wave is propagating from the default mode network. Actually, I have the results here. Yeah. Okay, so okay, this is the S operator. If you just look at this, you look at it here, or maybe okay, I have a better one. Yeah, this is better. So yeah, if you look at this, it seems like the V1 and the motor sensory area, maybe they're like phase leading, and then the frontal and the parietal, the precuneus, they seems like they're phase lagging. And this kind of phase lead lagging pattern between different functional network happens over a period of 20 time, and they are very slow. So we don't really end up with like, which comes first, which comes later. So it was okay. It was okay with EEG, and it was okay with the fMRI. But we might end up being in trouble with the really fast, like gamma waves from ECOG. That's something I could test for. Yeah, yeah, that's a
Cool.
good
Thank
point.
you so
Yeah,
much. That's great.
yeah.
Do we have any last questions?
This is great. Thank you so much.
I think it's time to let Joon-Young get some sleep. Um, I think all this is very interesting, especially showing the links, the ability to measure these kinds of patterns with scalp EEG and with the links to different kinds of individuals. I think there's uh, a lot of future directions here that are really exciting. So thank you so much. Everybody keep an eye. So get some sleep, Jun-Young. And everyone keep an eye out. Next month's Wave Club is going to be a presentation by Mark Kramer from BU. So he'll be here in February. So keep an eye out for that.
Okay.
Thank you,
Thank you very
everybody.
much. Yeah,
Take care, Jun-Young.
thank
Please be in
you.
touch.